Okay, so we've defined the likelihood, and we've discussed how we can use steepest descent to maximize that likelihood in the vector W. Here is a summary of the algorithm. We have as input our labeled training data, our labeled training pairs, so this should be a 1, and some step size that we set that's non-negative and close to 0. We'll initialize the vector to be a vector of zeros. So we'll initialize W to be a vector of zeros. Then for each iteration, what we do is we take the old value at iteration t, and we modify it by adding this vector to get the new value at iteration t plus 1, where this term is equal to the gradient evaluated at wt. And so how does this compare to the perceptron? Remember, for the perceptron, what we had here was something that looked very similar. The only difference was that we replaced this by first searching for a misclassified example, say that's the ith example, and then replacing the sum over those misclassified samples with just one randomly chosen one, because we were doing stochastic optimization for perceptron. However, remember that we discussed that we could have equivalently summed over all of the misclassified examples, so we could have a sum over all I that were misclassified, and that would be an equally valid and accurate algorithm. So in a sense, the difference between the perceptron algorithm and logistic regression is this term here. With perceptron, we simply did not have this term, and we were only summing over the misclassified examples. Now we sum over all of the examples, and we multiply each one by a term here. Notice that this term is going to be equal to 1, or it's going to become closer and closer to 1, the worse and worse our current model predicts that data point. So if our data, our labeled instance is +1, but our model, given the current vector W, is very confident in predicting -1, then this is going to be very close to 0, in which case we'll have something very close to 1 here. On the other side, if our labeled instance is, say, +1, and our model is very confident in predicting +1 for that instance, this will be very close to 1, and then we'll have something that's essentially equal to 0. So this value here that's pre-multiplying y times x is like a measure of how confident we are in our prediction. As we become more confident, we're going to have 0, so we're not going to want to change the hyperplane for the things that we get right, which means that for the instances that we very accurately predict, we don't want to modify the plane using that instance. But for the ones that we get very wrong, we want to use those instances to help guide and direct the hyperplane so that we can predict those values better. So in a sense, logistic regression has this fudge factor, if you will. It's simply a result of the probabilistic interpretation that we've given to the problem, whereas if you remember, perceptron had no such probabilistic interpretation at all. So there's one more issue, however, that we need to address, a potential issue that can come up with logistic regression, and this is the case where the data is able to be separated by a linear hyperplane perfectly. So we can find a hyperplane to cut through the data such that all of the +1s are on one side and all of the -1s are on the other side. In that case, if we did maximum likelihood for that model, what we could show is that the magnitude of W would blow up and go to infinity, because as W goes to infinity, it's going to make all of the data on the plus side. It's going to make the dot product between all the data on the plus side with that W become positive infinity, and it's going to make the dot product of all the data on the negative side with that vector W become -infinity. And in that sense, we can maximize the likelihood because we can predict that all the data on the +1 side are going to be +1 with probability 1, and all of the data on the -1 side are going to be -1 with probability 1. So there's no reason to have any uncertainty to use the uncertainty that the model gives us if we can do everything perfectly. So just as with the least squares case, where we made the transition to ridge regression, we can do the same thing here. We can add a regularization term that penalizes magnitudes of W becoming too big, and just like with regression, we can also motivate that as adding a multivariate Gaussian prior to the vector W, in which case we have, I should say, lambda over 2 times the dot product of W with itself as the additional term in the optimization where this corresponds to a Gaussian prior on W, in which case we're not doing maximum likelihood anymore. Remember that we're doing maximum a posteriori because we now have this additional prior term regularizing magnitudes of the vector W. So there's a parallel with regression. Remember, with regression, we saw that maximum likelihood and least squares had a certain relationship to each other. And then ridge regression was like MAP. And instead of doing MAP, we then discussed how we might want to find the posterior distribution of the unknown model parameter. And we found that we could do that with the Bayesian linear regression model. It was a multivariate Gaussian with a mean and a covariance. Now the question is, we've defined the likelihood model for the labels to be this sigmoid function, and we've defined a Gaussian prior on the coefficient vector W. We can do MAP for that, but can we do Bayesian inference? Can we find the posterior of W because we have defined a likelihood and a prior? So the answer we'll see is no, we can't calculate the posterior in closed form, which is going to motivate something called the Laplace approximation. So here's the problem that we're dealing with. We've again defined a Gaussian prior on the vector W, and we have this likelihood of independent sigmoid functions for the labels of an observation given the covariates and given W. So by Bayes' rule, we know that the posterior is equal to the likelihood term times the prior, and then we divide that by the integral of the numerator over the unknown model variable, in this case W. If we were to actually plug in a Gaussian density here and plug in the function, the sigmoid function here, and try to calculate the denominator in this case, we would quickly find that it's not a tractable integral, that we can't find this normalizing constant, and so we can't solve Bayes' rule and define and say what the posterior distribution is. So the next question in that case is, if we can't say what the posterior distribution is, can we somehow approximate it accurately?